Lab 2, Lines of Charge. The purpose for this lab was to determine the charge on a charged piece of tape and to create a new model that accurately displays the bottom piece of tape exerting an electric force on the top piece of tape for many different positions acting as a line charge. My results showed that the charge calculated from a point charge was smaller than it was when calculated as a line charge, and we know that the line charge calculation is more accurate. The charge calculated from a line charge was 5.4956 times 10 to the negative 9 coulombs. In this video, I will address the assumptions, measurements, results, and VPython code I used in the lab which allowed me to obtain these results. The main principles used in this lab are Coulomb's law, which allows us to use electric field and charge to find the electric force on an object using the given formula. The other principle is the law of superposition, which allows us to model the net electric field using multiple point charges. The assumptions that had to be made in order to complete the calculations for this lab. Charge was evenly distributed across the surface of the tape. Treat the tape as a multiple point charges. Neglect any outside forces besides the gravitational force and the electric force of the bottom tape on the top tape. The experimental procedures for this lab were very similar to Lab 1. However, the main difference for this lab is that we are not assuming a point charge model like we did in Lab 1. Instead, we are using a line charge model divided into a variable n pieces, and we calculate the electric forces derived from the electric field formula. The length, mass, distance between the tapes when they started floating, and the gravitational force on tape 1 were values attained from Lab 1. As stated before, the main difference in this lab was that we used the line charge model instead of the point charge model. We were given a starter code and had to edit it to create a model with a line charge of tape. First, I added the constants, the mass of the tape, the new charge, which was calculated by changing the charge once the code was complete until the electric force and the gravitational force were equal, and the electric field function that was created in Lab 0. Here the code creates the tape 1 and tape 2 models. N is the value used to divide the tape into more or less pieces, and I chose to use 10 pieces. The larger the N value is, the more accurate the calculation of the charge will be. This part of the code takes each individual piece of tape and calculates the electric force of the pieces and then sums them all up to get the magnitude of the electric force. Here I changed the scales, which changed the size of the vectors to show up on the model. The for loop shows the electric force acting on each individual point charge within the line charge, and instead of having only one arrow for electric force as in Lab 1, I also have individual force arrows. The last part is to print out the magnitude of the electric forces as well as to show the electric force and the gravitational force vectors. We take the electric field from each blue piece onto the red piece and sum them up to get the green arrow. Thus, the green arrow represents the electric force of the individual pieces. The white arrow is the summation of all the green arrows together, which is the sum of the electric force. The yellow arrow represents the gravitational force. You can also see at the bottom that the electric force and the gravitational force are equal to each other, which means that the charge shown earlier in the code is correct. Question 1. The point charge value is smaller than the line charge value calculated in this lab, which means that the point charge way of calculating gives an underestimation for what the charge is going to be. The larger the n value, the larger the line value gets, so the summation becomes more accurate the more numbers you break up the tape into. Question 2. The line charge value is more likely to be closer to the real value. This is because it uses summation and breaks the tape into smaller charges, thus allows for a closer approximation of charge. To be more accurate, the tape would have to be broken into infinitesimal pieces. In conclusion, the fundamental physical principles used in this lab were the law of superposition and Coulomb's law. The results of this lab demonstrated that the charge on a charged piece of tape to be 5.49560 times 10 to the negative 9 coulombs. The magnitude of the electric force on this tape was calculated to be approximately 2.01792 times 10 to the negative 3 newtons by the computational model.